So I'm going to be talking about simple number theory in Perl 6. Number theory, the fundamental branch of mathematics, studying the properties of integers. It is certainly fundamental in modern cryptography. Perl 6, I don't really need to talk a lot about what Perl 6 is here, sister language to Perl 5. A lot of this is conference-driven development. That is, I've done a little bit of work with Perl 6 and wanted to do some more, so this is a way to force myself to do that. So I am Dana Jacobson. I'm coming from Portland, Oregon, the United States. Come to FOSDEM a couple times, love it here. Number theory for me is a hobby that got out of hand. I imagine lots of you guys have had something similar. So nice things about Perl 6. We've all heard there's lots of ways to do something in Perl 5. There's more than one way to do it. Perl 6, here's this, says, laugh, hold my drink. I'll tell you. Perl 6 has so many ways to do things. A lot of them are really nice. For me, everyone's going to have a different set of features they like. Damian Conway talked about how he just loves using Unicode characters in his programs. I'm from the United States. I don't know what he's talking about. So Jeff and some other people, Brian, are looking at grammars. I haven't looked at grammars, but it has something for everybody. I love big ints, native to Perl 6. In C code and in Perl code, you're constantly fighting with this issue of when my numbers start getting large, weird things start happening. We have rationals. I don't actually care so much about them. I know a lot of people love having the idea of rationals where I can just maintain this idea of it's 1 over 3, not immediately turn that into 0.333 something, not 3. Junctions are pretty cool. exp mod is a wonderful feature. It's a function I end up writing in every other language because when you want to raise a to the kth power, mod n, that's a terrible way to do it if you actually raise a to the kth power and then mod n, because you end up with a humongous number, and there are much faster ways to do it. Perl 6 has it completely built in. Perl 6 also decided that, hey, this idea of is a number prime is pretty fundamental, and people keep writing it in every language, so we're just going to toss it in. That's nice. We get a bunch of other little functions. Pick is surprisingly useful. You take a list and just say, give me a random element from it. It has lots of variations. It is used all over the place. So let me start with this very simple RSA example. We're going to generate a key. So we want to generate a couple random primes. N is the product of the two. I think, yeah. So we choose, take the LCM of the totient, which because they're prime is very easy. We choose an E, we get our D. Let me go through the Perl 6 code for this. Generate random primes. It's really, really simple, except my is prime ran off the screen there. So we just take, we have a number of bits. We just keep taking random numbers until it's prime. And there we go. Now we can fill up P and Q very easily. These are very simple. Oh wait, but Perl 6 has LCM built in, the least common multiple. So I want to choose an E. There's a different way to do this. If you want, you could just pick an E that's coprime. This is a different way to do it. You go ahead and pick a random one. And we get to use our GCD function. And again, our pick just says, just give me a random value from that. We do it until it's coprime. So now we want D, which is going to be our private key. We want the inverse of that. The idea is D times E ends up being 1 mod phi. So how do we do that in other languages? Well, we get to write a routine to do it. But in Perl 6, well, we have this exp mod. Just give it -1. It'll give you the inverse. It's surprisingly handy. This is really short code compared to what we end up with writing in other languages. And we decided to use 1024 bits. Perl 6 has no problem with this whatsoever. My talk is not going to be about cryptography, so I'm going to leave aside all of the math, reasons why, and the boilerplate code you would normally add to actually make this a useful routine. You can look that up. So binomial is very common. We want to find the number of combinations taking 50 items, for instance, I want 50 items and I want to choose combinations of 10 of those. How many do I have? I add .elms and I get this humongous number. Well, I sure am glad I didn't iterate over that. Perl 6 is very clever and knows that, in fact, you're just asking for the number of elements. You didn't want me to create this huge list with this many items in it. You didn't want an iterator. You just wanted the number of elements. So Perl 6 gives that to me. This is a formula for how you calculate that. If you dig through the Perl 6 internals, this is the product of n times n minus 1, n minus 2, and so on. We divide by the factorial of k. If you dig through the Perl 6 code, you find basically this in Perl 6. First we have n down to 0. This is a zip operator. So we're going to take this second list, which has a little optimization in it for the minimum, and we do the divides. And finally, we get to reduce it. We just say star here, and it says multiply everything together. Now, in these ended up being rationals. So in most languages, you end up having to write a whole lot of code to deal with this. It's not complicated code, but you have to keep in mind, oh wait, I have to make sure those divides are all integers. In Perl 6, we don't really care. We just write the routine just like we would like to. Here's binomial in C. This is a pretty standard way to do it. Mark Jason Dominus had this on his blog in 2007. Well, not this, but something like it. And said, this is how you should do binomial. It has no overflow problems. It's great. Except it does overflow. Someone found he posted this on Reddit, and someone said, oh, actually, it does overflow. Now, probably most of you will see the obvious way to fix it. So this is how you fix it in C. It's actually very fast. It's clear. Everybody would do this, and you completely understand why this works. Until you realize this is still only for 64-bit. If I go past 64-bit, I have to start getting into big int libraries and portability issues and so on. Perl 6, solves it all. So now I'm going to talk a little bit about primes. Why primes? Well, okay, some of you who know me are wondering, have you ever given a talk where you did not say the word prime? And yes, but it was about a decade ago. Primes are really important in number theory. They are the atoms for the integers, if you will. There are a lot of algorithms. In fact, that binomial algorithm you can do faster if you say, well, I don't actually have to know all the numbers up to n. I can just go over the primes, so I can speed things up. There are a lot of algorithms in number theory where it turns out you don't actually have to go up, for instance, solve to n. You can factor n, perform your operations on the prime factors, and then combine them. And you come up with much faster ways. So there are three things we generally want to do: generate primes, recognize primes, and factor integers. We don't factor primes. So the usual way of generating primes is the thief of Eratosthenes, who wrote about this in about 250 BC. He was the chief librarian of Alexandria. He wrote in all sorts of different areas. He contributed to many, many, many fields. Unfortunately, all his works were lost when the library burned. But lots of people wrote about the things he did, including this algorithm. And interestingly, there are some new sieves that have come out in the 20th century. They're all slower than this. They have some interesting properties. The sieve of Atkin actually is slower than the sieve of Eratosthenes. I'm going to talk about just the very basic monolithic, non-segmented sieve. You can get complicated, start adding optimizations. Like everything, you can spend a year adding optimizations. So very simply, we enumerate all our numbers from 2 to n. I've chosen 120. We pick the first one and say, that one's prime, because they all kind of look prime right now. And we know that 3 is as well, because we know everything up to 2 squared is prime. And we just mark all the evens, because we know they're all multiples of 2. So then we can move on to the next one, which is 3. And we're going to mark all the multiples of 3. Because I've chosen 15 here, they're all going to line up. We can do the same thing for 5s. Notice that I start at 5 squared because everything up to that has already been marked. We go up to 7. And it turns out at that point we're done because 11 squared is 121. So there wasn't a whole lot of operation going on to generate these primes. On Wikipedia you'll find the pseudocode, which it turns out seems to be remarkably hard for people to implement. It's 4 lines. We go up to the square root of n. We ask if it's prime, if this number is prime so far, and we go from I squared up, counting by n. So there's an operation that is not done in here, which is remainder or divide. It's a very efficient algorithm because the only thing going on is marking and adding. So in C, we're not going to go over this very long, but basically it's exactly the same thing as the C. Here's our 4 lines. We can argue about I times I versus taking the integer square root. But there's your 4 lines. And then we go through and we can do that. Perl 5, in this case I've done an additional optimization of only going through the odds. That is, we saw most of that work was at the very beginning where we had to mark all the odds. Well, after 2, we know we don't have to deal with them at all, so we're just going to ignore them. So this is not very Perly code, but it is exactly the same as that C code or the Wikipedia. But in this case, we skip the odds. There is a bit of wonkiness at the end where we're doing a map and grep to turn those odds back into the numbers we care about. So we use half the memory by doing this. So on Rosetta code, I looked last year, and it was kind of partly the reason for this. I said there are 3 examples of the sieve of Eratosthenes on Rosetta code, and all of them are wrong. So they start out okay. They say 0 and 1, not prime. Everything else prime. Looks prime so far. We do a gather. This is a cool feature where we take the key value. We just say I want the actual number, and then I want the value that's in that array. So I can get them both at the same time. And then we do, oh, well, if it looks prime, then take the number. But wait, what is this doing? That's a mod operator. So for every number from n squared up to n, I'm going and checking the divisibility. I'm basically doing trial division on every number repeatedly. So there's a simple solution. Now we have the sieve of Eratosthenes in Perl 6. Looks exactly like the C code, or like the Perl 5 code, or the Wikipedia pseudocode. And it runs significantly faster. So Perl 6 has a lot of different ways to do these things. We can try doing it using a set. This is something someone put on Rosetta code as well. Doing it with a set. We have our multiples. We're going to gather. Unless multiples contains the number, we take it and we do a set union. You can use fancy Unicode characters for the contains and union. Basically, we're making a new set with number squared, that plus number, and so on, which is exactly what we wanted from that pseudocode. You could change it to, is the number an element of the set? Is the number intersected with the set? We can go straight to exists key. Lots of ways to do it. We also have this isPrime operator, so we could just do, well, I'm just going to walk all the numbers and ask if it's isPrime. That's not a sieve, but isPrime is built in, so maybe that's fast, and it's certainly easy. It's so easy you could just do basically grep isPrime through a list. So the set operator, so that code has some significant problems with it, and also Perl 6's sets haven't been optimized entirely, so we're going to ignore that. But here's our trial division. It took 401 seconds to generate the primes to 1 million, which is absurdly slow. So we know doing trial division, basically the incorrect sieve of Eratosthenes is the wrong way to do it. Here's the isPrime version. Okay, so I wrote a new version of isPrime. I went to more VM and started writing C code. And so there's a new version of isPrime, and I'll talk about that more later, which is significantly faster, and it's faster at all sizes. So hopefully I will actually get that pushed out soon. So our sieve, actually, when you fix the sieve, instead of doing this kind of broken sieve, you do the real one, it's looking pretty good. You can do odds only. I didn't show that example, but you can speed that up some more. That's looking good. If you increase this, it would start looking better. Perl 5 has had, what, 20-something years of additional optimization. And we're marking and adding. This is absolutely what C loves to do. So this is a little bit of an unfair example here because this is so simple. But we've chosen something very, very simple to try out. And see, there are lots of ways to do it in Perl 6, and you can speed it up. And in fact, you could certainly call C code from Perl 6 if you wanted to. So we're moving on to the next one. How do we recognize a prime? Well, we can do trial division, which is actually really good for numbers up to 1,000 or 1,000,000. But if I give you a 64-bit number and say, hey, try dividing by all the numbers up to the square root of n, or if I give you a 1,000-digit number, you're never going to finish. It's really slow. Miller came up with this method in about 1975, which is very efficient and answers the question entirely of whether a number is prime. There's a bit of a problem. Step 1, prove the Riemann hypothesis. So this has been giving us a bit of a bother for the last 150 years. So that doesn't really work very well. We can do special forms, Mersenne numbers or Proth numbers, that is numbers that are 2 to the n minus 1 or 2 to the k times 2 to the n plus 1. We have some really efficient ways to do it. But that only works for numbers of that sort. If you like finding large Mersenne primes, then that's nice, but that's not very useful for most people. We can do partial factoring methods. This is really what was used up to, well, in the 1800s, 1900s, up to 1980s, where I take n minus 1. I want to find out if n is prime. I take n minus 1 or n plus 1, and I perform some factoring on it. I don't have to completely factor the number, but I have to do some factoring. It turns out we did primality fairly well. That method works quite well up to about 40 digits. Starts getting slower, and eventually you just can't find factors. So in the 1990s, there were a couple methods that are quite efficient, APRCL and ECPP. APRCL are the initials of the people who created the algorithm. ECPP is elliptic curve primality proving. I think there are two reasons people normally don't use these. One is computer programmers don't usually know that they exist. And two is they're complicated. Perl 5 has one of the, in the N-theory module, has one of the only implementations of ECPP out there that's open source, certainly the fastest. And hopefully Perl 6 will get one soon. So because these are hard, we come up with this idea of a probable prime. So what to do to find a probable prime? You find some property that all primes have and that most composites don't have. Well, if lots of composites have it, then it's not a very useful test. But if all primes have this property and very few composites have, then this is actually fairly useful. And this is quite commonly used. So the common return values are 0, definitely composite, 1 is probably prime. Sometimes we'll add something for definitely prime. And minus 1 is the, if these are your only responses and you have, for instance, you're doing a Lucas-Lehmer test and it's not a Mersenne number, well, you can't return anything here. It's the wrong form. You don't know what it is. No small divisors. We're going to give some little Perl 6 code here. This is a particularly bad one. This just says, are you divisible by 2 or 3? If not, I don't know, you look kind of prime. Most humans go something like this. They might go with 5 as well. Do something like this. I don't know, it looks kind of prime. So this is kind of neat, these junctions where we can basically just, instead of saying n equals 2 or n equals 3 or and so on, we get to just say n equals 2 or 3. Here's the mod 30 version of it. All primes past 5 are going to have this property. This gets kind of messy in most languages. Junctions make this really simple. and easy to read. Oh, if the remainder after 30 is this, great. So Fermat, I was just in France and they were telling me, yes, it is Fermat and Lucas. In the United States, it's either Fermat or Fermat. If I said Lucas in the United States, no one would have a clue who I was talking about. It's Lucas there. But so Fermat came up with this little theorem which says if we take an A between 2 and p minus 1 and we raise it to the p minus 1 power, and if p is prime, it's 1 mod p. All primes have this property. Some composites do. Most don't. So here in Perl 6, this is a bunch of boilerplate, mainly having to do with small numbers, and you could add restrictions for making sure your base doesn't exceed, it doesn't go out of range. I've decided to try to make that work. It's kind of irrelevant. Wow, that's easy. EXP mod. So there is a problem. Carmichael came up and said, hey, there's this class of numbers where this is true for some composites. This is true for every base. So you will never be able to figure out those numbers are prime or composite because they look prime based on this test. So Euler published a few papers. And one of the things he came up with was, well, we can improve this test. So we're going to have now, it is p minus 1 divided by 2 is plus or minus 1. And same boilerplate, but there we go. Note the shift operator is plus, the bitwise shift operator plus greater than. We can use our junction again, very easy. Euler also went and said, yeah, but it's not just plus or minus 1, it's equal to the Jacobi symbol. What's the Jacobi symbol? So Legendre came up with this idea even earlier and said, well, this symbol, and it's surprisingly useful in number theory, is 0 if it evenly divides p. It is 1 if it is a quadratic residue, that is, if there is a number that exists that it's a square, mod p, and minus 1 otherwise. So here's a crazy version of Legendre symbol. In Perl 6, we've used an infix operator with a special pipe. We've made Damien happy by using italicized characters, and they're sigilless. And we're using a given when. So unfortunately, this particular form doesn't help us much because we're already going through the same operation. The Jacobi symbol is basically the product of that for factors, but you don't have to factor, and you can do this. This is kind of ugly code, but it exists. You'll see the same code in lots of languages. So now once we have that, very simple Euler-Jacobi in Perl 6. We mod n because we're going to get back a 1 or minus 1, so this is a simple way to do it. And all of a sudden our Carmichael numbers go away. This test, if you run random A values, it turns out that no more than half of the A values are going to work for any composite. So Solovey and Strawson made this a primality test. You've probably heard of the Miller-Rabin test. This came first. And now we'll go to Miller-Rabin. You may have seen this before. We take n minus 1, basically take out the odd part, and run this routine. I'm not going to go over the math behind it, but that one also has no Carmichael numbers, is classically used. This looks exactly like C code you will find everywhere for this. So in Perl 6, we have this idea that, well, the chance of being a composite, passing this test, is 1/4. And if you use random bases, then your chance is 4 to the minus k, which goes very small very quickly. And Perl 6 says we'll use 100 bases for this. This is a great idea. No. So the reason why this is not a good idea is actually twofold. The number one is in more VM, it uses libtom math, and libtom math does not use random bases. It uses the first 100 prime bases, which sounds great until you find out that in 1994, someone published a paper which showed you how to generate counterexamples to this. So this is a particular number that he published. There's an algorithm to generate these. And Perl 6 will tell you that this is prime. It is not prime. There are ways to fix this. We'll talk about that in a minute. The other thing is using 100 of these tests is a significant overkill. We don't need to do that many tests. So that's a performance issue. And this was a common method in the 1980s. Early 90s, some people published papers and said, you know, this is really problematic for a number of reasons. So Perl 6 used to have in the language specification that isPrime took a parameter of the number of trials for Miller-Rabin, which I particularly disliked because it put implementation details into the language itself. Fortunately, that was all removed before the language came out, so we can apply better methods without changing the API, as long as we do the right thing. So the BPSW test is the way that most people have standardized on. You do a single Miller-Rabin test, and you do a Lucas test, hopefully a strong test. This is my wall of text that I should not do in talks. It was published in 1980. It is deterministic for all 64-bit numbers. No counterexamples have been found. There are at least 2 theses where people worked hard on trying to find counterexamples using very clever math to say, well, I'm sure that this set contains it. The only problem is this set is of size 2 to the 1,000 something. And so one of those numbers in that set might be a counterexample. So we haven't found that yet. Almost all math programs use this, and Go, Julia, and Python modules have all started moving to this. So I have an implementation in MoreVM for this, and it should be pretty easy to put it in JVM as well. And it's faster. So I'm going to do a couple of methods for factoring. I'm not going to talk about all of these. Trial division, very straightforward. Fermat, busy guy, also came up with a method for factoring. Pollard has his row method, and P-1, very common. Square form factorization, ECM, quadratic sieve, and NFS are all commonly used. NFS is generally a PhD level I think there are 2 implementations out there. Certainly I'm not going to show you an implementation. It would be tens of thousands of lines. So trial division, Damien showed an example in his talk. The primary difference here is just that when you find a factor, you need to, your new composite, you need to start looking less, I guess I should say. A lot of the examples do not do this test of redoing the limit, and so they do a lot more work. This is useful for small numbers. Fermat, we did basically, we're looking for differences of squares. All odd numbers can be represented as differences of squares. Fermat said, hey, if there are 2 factors are close to each other, we can find this fairly quickly. But we have this is perfect square predicate. So how do you find perfect squares? That is a number that is, s times s equals n. Is n a perfect square? So you'd think, oh, well, I can just write it like this. I have big numbers, so big ints. Great, I just take the square root of n, turn that into an integer, and see if that returns that. But we then realize Perl 6 does not have big floating point numbers, so that actually doesn't work. So the right thing to do is write an integer square root routine. I did not do that yet. About 64 or 53 bits, this starts failing. It's just like C, just like Perl 5. This is a way to solve the problem. It's fine for 64-bit. It gets very, very slow. This is the wrong way to do it, or it's an inefficient way to do it. So some other people have said you can actually do some tests. You can actually quickly look at a number and find out for some simple properties, is it possible that this is a perfect square? So we can run that final test less often. If square root is really expensive, you can do some very simple math to avoid it. You can also be clever with bits and do it. Notice the shifting, the bitwise and is a little different in Perl 6. You can go totally crazy. if square roots are really expensive, and you can continue this process. These are using Bloom filters, which are basically a way of filtering out anything that isn't going to be possible using different simple divisors. So Pollard row, Damien showed this example. This is with Brent's cycle optimization. Damien said that this was called the row algorithm because it uses a variable called row. It doesn't use a variable called row, and that's not at all the reason why that's named that. That's a really fuzzy image. The idea is we're trying to use the birthday paradox to find examples where we can find a collision. So we have two processes running, one going slow, one going fast, and the idea is when can we find an example where they correspond. And if you graph this out, somebody said, well, it looks kind of like a row symbol, and that's why it's called Pollard's row. And it is really, really fast at finding small factors. And when I say small, I mean, say 8 digits, 10 digits. It doesn't matter how big your number is. If it has a small factor, under 10 digits, this is going to be extremely fast at finding it. So it's not useful for solving RSA cryptography. If your keys were generated correctly, you have 2 very, very large factors. Not going to work at all. But for small factors, this is really common. And this is Pollard's P-1 algorithm. Was trivial to write straight from Wikipedia into Perl 6. It basically says, well, maybe I'm having a hard time factoring n, but what if n minus 1 has a lot of small factors? And if it does, we can factor n very quickly. And that pretty much concludes my talk on Perl 6 and number theory.